In an atom, we know that there's different energy levels. And those energy levels are the levels around the nucleus. So, in an atom, you're going to have a nucleus that contains all of your protons and neutrons. And then outside that nucleus are the different energy levels. And these are the levels where the electrons live. And they each have a designated area. They're told you live on level 1 or you live on level 2. And either way, these electrons float around in their level, and that's where they live. Now, do they have to stay there? Yes and no. Yes, that's their designated level, and they do have to stay there unless something happens. And that something happens is added energy. So, in these different energy levels we have, the electrons can move. Now, the higher the energy level, the more energy. So what happens? We have an electron sitting here at energy level 1. There it is. Now something's going to happen to this atom, like whether it gets exposed to electricity, because that's probably the most common thing. If electricity runs through this atom, then energy is being given to this atom, specifically to all of the electrons. This electron's going to jump up and absorb that energy. It's going to jump up to one energy level. We don't know which one, but it's going to jump up to one of them. Now, eventually, it's like, it's like uncomfortable at that state. It's like it has too much energy that it can hold. So it can't stay there permanently. It has its region. It's designated to live at energy level 1. So eventually, that electron is going to come back down. When it comes back down, it's going to release energy. And what is that energy that's being released? It's a wave. It's specifically an electromagnetic wave. So that energy that's released is a wave. It's a wave of energy. So it has energy. It has a frequency. And it has a wavelength. And this particle, this thing that's being released that has energy, frequency, and a wavelength, it is a photon, which is light energy released. Okay. It has these three things. Now, the energy, the frequency, and the wavelength are all specific to that atom. Or, specific to that wave. So whatever amount of energy it has, it's going to translate to a specific frequency and a specific wavelength. And they're all related. They're all related very much. Okay, so what do we do now? There are some equations that will relate this situation. So anyhow, these electrons continually jump up and down. Maybe this one on energy level 2 jumps up and down. And when it releases a specific amount of energy. And maybe there's one that's on level 1 that jumps all the way up to level 5 and then jumps down. It releases a specific amount of energy. So all of these energies are very specific. They're not random numbers, because when it jumps a specific distance, and that specific distance relates back to a specific energy. So it's like an exact number that it's jumping when it does jump. All right, so let's start this off then. Let me get some clean paper here for you. Okay, so okay, this will be exactly like what we did on Tuesday and Monday. The only difference is how the specific numbers we're going to use. So we're going to be calculating wavelength and frequency. Now, specifically, the waves on the electromagnetic spectrum, so electromagnetic, EM waves, always travel at that's 300 million meters per second, and that is the speed of light. at 300 million meters per second. So, to calculate wavelength and frequency, if you remember, we had S equals lambda F, where S is the speed, lambda is the wavelength, and F is the frequency. Now, the only difference is we now automatically know what the speed is. It will always be this value. In this case, when we're talking about electromagnetic waves. So, I'm thinking of a specific scenario. Let's think, what if we have a wavelength? What is the wavelength of a wave with a frequency of 3.76 times 10 to the 14th hertz. Now what you're going to see is that these numbers on this electromagnetic spectrum are really, really large numbers. Like the frequency of one of this electromagnetic radiation, it's huge numbers. 10 to the 14th, that's 14 zeros, or 14 decimal places this was put on. Don't let that bother you. You were able to solve these the other day perfectly, so don't let these numbers bother you. All we're going to do is rearrange this formula to suit our needs here. So, in order to solve for wavelength, we're going to rearrange this. S equals lambda F. Let's get rid of the frequency. And we're going to have lambda equals speed over frequency. Now, we should have speed and frequency. We're going to plug them in. The speed is automatically the 3.00 times 10 to the 8th meters per second. And the frequency is 3.76 times 10 to the 14th hertz. All right, so you would divide those out, and you're going to see that this is an incredibly small number. If you divide this, you should get 7.98 times 10 to the negative 7th meters. Okay, so you would just use a calculator. Now, you could very well make a mistake when doing this calculation, so you must always show me this part of it. Show me what the setup's going to look like. Okay, and you're going to always write out what you have here. That's how you would solve this if you were looking for wavelength and you were given frequency. You divide it out. Now, could we also do this? What if we were given frequency and we want to find wavelength? Oh, I said that backwards. Excuse me. What if we were given wavelength and wanted to find frequency? We could do the exact same thing. Now, let me give you another scenario. Okay, what is the frequency of a 6.9 times 10 to the negative 13th meter wave? Now this is a very small wave. We're talking probably like gamma or X-ray, very, very, very small, very high energy. And we want to know what would be the frequency of a wave like this. Well, we can figure that out. We know our formula. We can do our math. So, we start off with S equals lambda F, and this time we want to find frequency. So we're going to divide this out. Now once you do this once and we have these divided out, you don't have to keep doing this. Just go right to this step. You'll have the equation already ready. Or in this case, frequency equals speed divided by wavelength. So you can jump right to that side, this step, once you have the equation. Anyhow, let's plug in the values we have. We know that the speed of any of these waves is going to be 3.00 times 10 to the 8th meters per second. And the wavelength is 6.9 times 10 to the negative 13th meters. So we have to divide that out, and we'll get our answer. When we divide this, we will get 4.4 times 10 to the 20th, and that's hertz. That's the frequency. So this is an incredibly high energy, very high frequency wave. So once we do this once, we now have an equation to solve for wavelength. We now have an equation to solve for frequency. The speed will always be 3.00 times 10 to the 8th meters per second when you are dealing with electromagnetic waves. So we've done the first two on the paper. You can continue the rest of them and complete them on your own. We will go over them tomorrow, so keep this paper with you.